Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we talk about all things Gen Chem related. On this video, I'll be introducing how to do Lewis structures for ionic compounds. Let's get started. So if you recall in the previous video, we talked about how when we're drawing these Lewis symbols, we're going to start off by looking at the number of valence electrons that an atom has. Well, we still start with that information when we're developing Lewis symbols for ions, but just then bearing in mind if it's a cation, we'll be taking away electrons, and if it's an anion, we'll be adding additional electrons to create that charge. And so with the cations, what you would be expecting is that you would end up with a completely empty shell. Like look at lithium, where we've actually kicked out an electron. And then with your anions, you would have a completely full shell where you now have something like fluorine, which is shown to you on the right. Now make sure whenever you are gaining or losing electrons that you do indicate the charge where appropriate. So some things we know as things are becoming ions. Well, first, we know that the noble gases are the least reactive group of all of our elements. And we also know that as elements are trying to generate these ions, whether it be the metals that are losing their electrons or the nonmetals that are gaining electrons, they're ultimately trying to obtain that noble gas configuration. If you don't remember that, go back to the video back in chapter 8 where we talked about those things. Now, for your metals, as they are losing their electrons, remember they're going to be taking on the noble gas configuration of the noble gas that is before it. For your nonmetals, they'll be taking on the configuration of the noble gas that comes after it. And so we can see here in this situation where we have elements such as sodium or magnesium that ultimately want to lose their electrons, like as you see here, where you're kicking out that valence shell. They ultimately end up taking on the electron configuration of the noble gas that comes before it. And then similarly with our nonmetals, where they're gaining electrons, they're going to take on the noble gas configuration that comes after. Remember that noble gas configuration is the most stable, and so that's what everyone is trying to obtain. So atoms are going to bond because at the end of the day, they're looking for a more stable electron configuration. The more stable it is, the lower the potential energy, and thus the overall more stability that that atom or molecule now has. And so bonds are going to occur, as we mentioned before, through either transferring or sharing of electrons. And typically when this does happen, you're going to result in having that outermost shell with 8 electrons. Or similarly, if you're like a metal where you've kicked out an electron, well, what's remaining, that empty shell is there, and then there's a full shell that is under there in that core. And so as we are developing these structures, just keep that rule of 8 in mind, or the octet rule, as you're going forth. Now, our octet rule basically says that atoms are going to do a multitude of things to obtain this octet rule. They may gain or lose electrons, or they may ultimately share electrons. But the end result is that they end up with that noble gas configuration with a full S and a full P subshell. Now, there are a few exceptions to these rules. Of course, we'll highlight some of them. There are a few elements that can have less than 8, and those are shown for you here with hydrogen, lithium, beryllium, or boron. And then there are also several that can have more than 8, and that's what we know as the octet expansion rule. Now, the octet expansion rule only applies to elements that are found in period 3 or lower. And so when I say period 3 or lower, remember your periods, those are your rows, all right? And so when I'm saying period 3 or lower, that means period 3 or lower on the periodic table. And well, why is that? Well, remember, in that third energy level, that's when those D subshells come into play. However, they're not filled at that time. So you have these empty D subshells that can actually hold more electrons. And so when we're developing these Lewis structures down the line, just keep that rule in mind that some elements can have more than 8 if they are found in period 3 or row 3 or lower. Now with ionic bonding, we're going to be showing that actual transfer of electrons that happens. We won't be showing a bond, a line connecting the different atoms that are there. But instead, we're going to show that metal that's losing electrons and the nonmetal that's gaining electrons, and ultimately adjust the charges accordingly. And so in the example of lithium and fluorine coming together, well, we know lithium is a group 1 metal, so it's going to kick that electron out. We know fluorine is group 7, and so it's going to want to accept that electron. And so as that process occurs, lithium would then take on a positive charge, fluorine would take on a negative charge, and that positive and negative entity would be attracted to each other. Now, this is nothing new that we haven't seen before. We saw this back in chapter 2 when we were predicting the formulas of ionic compounds. And so we saw before where lithium we would say is group 1, so it has a positive charge. Fluorine is group 7, so it has a negative charge. Crisscross the charges down, and you can end up with the formula for the compound of LiF. Okay, so now we're putting the why behind what we know is happening. And so there are a couple predictions that are out there about what would happen with ionic bonding. And so Lewis theory does predict the number of electrons that a metal atom could lose or a nonmetal could gain will be based on obtaining that stable electron arrangement or getting to that octet rule. And so this really helps us to predict the overall formula for these ionic compounds. So when we're predicting the ionic formula for these compounds, we can use the Lewis symbols along the way. The electrons are going to be shown to be transferred from the metal to the nonmetal, and we adjust the charges as necessary. So for instance, if we had something like lithium and oxygen coming together, well, again, think about it. We know lithium is a group 1 metal. It wants to kick out an electron. We know oxygen is a group 6 nonmetal, so it wants to take on additional electrons. Now, if that lithium were to get rid of its electron and give it to oxygen, well, that's great. It would get lithium empty, but it wouldn't satisfy oxygen. So we would ultimately need to adjust the number of lithiums that we have available in order to balance this out. And so we would end up with 2 lithiums that are present that are both losing their electrons and giving them to oxygen so that oxygen can become completely full and take on that -2 charge. As a result, we could then say that we have 2 lithium cations and 1 oxygen anion, and then the overall formula would end up being lithium Li2O. Again, nothing new that we haven't seen before. We have always said that lithium is +1, oxygen is 2-, crisscross down, and that would be our formula. Okay, again, putting the why behind what we know. All right, so let's try an example here. So it says, using the Lewis theory, let's predict the chemical formula for these ionic compounds. So predict the formula for a compound that contains calcium and chlorine. Well, we know calcium has 2 valence electrons, it's group 2. Chlorine has 7 because it is in group 7. And so we know that calcium would be able to transfer at least 1 electron to that chlorine that is present. But we would not have enough. We would need an additional chlorine to be able to take that additional electron from that calcium ion. As a result, we would then end up getting an overall formula of calcium with 2 chlorine ions, or calcium chloride, CaCl2. Okay. All right, and so let's put this all to practice. So it says, use Lewis symbols to predict the formula for an ionic compound made from reacting a metal that has 2 valence electrons with a nonmetal that has 5 valence electrons. So if we think about that, regardless of knowing what element it is, we know that this metal has 2 valence electrons and that our nonmetal has 5. And so we can now see where we can transfer to. Well, we could say that our metal could give away its 2 electrons to the nonmetal. So we would have a 2+ charge, but we don't have enough at this point. Our X still is not stable. So we would need another metal that also starts with 2 valence electrons, and it can now give 1 to that nonmetal. But now our metal has nowhere else to continue to donate. So that means we need another nonmetal, which also starts with 5 valence electrons. Well, now I can give that metal electron to my nonmetal. the metal would take on a +2 charge. But now I realize, hey, I need one more metal with its 2 electrons that can be then donated to my nonmetal to make that stable, with the end result having that 2+ charge for my metal and both of my nonmetals now having a 3- charge. So with that in mind, we can now see that this molecule, or this compound, excuse me, not molecule, would have 3 metals present, 3 metal ions for every 2 nonmetal cations. So we could say that we have 3 metals and 2 of our nonmetals. And again, I'm just using X's and O's to help you track what's happening. So the end formula would end up being M3X2. And again, we would have always done that if we knew before that the metal had a 2+ charge, the nonmetal had a 3-. We crisscross down to get our formulas. Now, some things we want to bear in mind with ionic bonding is that ionic molecules, individual molecules, do not exist. And the reason that is because the electrostatic attraction that's present is non-directional. So you have these positive and negative ions that are all around. And so rather than getting this individual discrete molecule, we end up with that repeating positive and negative crystal lattice structure that we've seen shown for us before. Now, when we report the chemical formula is just simply the empirical formula of the ions to one another. And so we've seen this image before where we see that the positive and negatives, they're going to create this crystal lattice structure that has this repeating pattern present. Now, there are a few properties associated with ionic compounds. We'll get into the why these compounds exist in chapter 11. But some of the things to remember with ionic compounds do tend to have very high melting and boiling points compared to our molecular compounds. Now, they can also have the ability to actually conduct electricity when placed into the liquid form. As a solid or liquid, they could actually act as a thermal insulator. They tend to be hard or brittle when they're solid, so think like salt. And they're soluble in water and are able to conduct electricity through those solutions. Now, if we look at the model versus reality, the Lewis theory tells us that in the liquid state or when dissolved in water, ions have the ability to move around and thus should be creating these positive and negative charges that are floating around in solution. And as a result, you would expect they can conduct electricity. Well, the reality is we do indeed see that. When ionic compounds are dissolved in water, that dissociation process happens where the positive and negative ions are now floating in solution, and they do have the ability to now conduct electricity in that solution. A great example of this conductivity process is shown with sodium chloride. So if you've ever taken a physics class, you may have done this demo or exercise in class. But if you had solid sodium chloride, by itself, those ions are locked in position. However, once we place it into solution, once we place it into water, we know that ionization happens. The positive and negative separate from one another. And as a result, those positive and negative species that are present can be attracted to the different electrodes and ultimately allow conduction of water. And so this phenomenon is something that is observed with different ionic compounds. I hope this video helped you to understand ionic compounds and how to draw Lewis structures with them. Make sure you guys like, comment, and subscribe, and let me know what other content you'd like to see. Come back for more videos, and I'll see you guys later. Have a great day. Bye-bye.